Hello and welcome back. Last 4 videos we spoke about linear regression with one variable. Meaning that we tried to predict something based on one variable or feature. Like for example with this training set, where we tried to make a hypothesis that predicts the price of a car based on the amount of horsepower the car has. So we had one variable, namely the amount of horsepower. For example, if we plot these points on a graph, we get this. Now our goal is to draw a linear line that fits the data best and that will give accurate predictions for new unseen data. So after we trained the model and decided that this is the best hypothesis, we can now try to predict the price given some new unseen data point. For example, we can estimate the price of a car to be around $25,000 given that the amount of horsepower is 83. However, if we think about it, we can give more information than only the amount of horsepower. This extra information will then give us even more accurate predictions. Say for example that you want to predict the price of a car based on the amount of horsepower, the age of the car and the mileage of a car. This gives you way more information about the car than we had before and thus will allow us to make more accurate predicts. But before we will see how this is done, we need to get familiar with some new terminology. First of all, we no longer can just refer the input variables as x. X will now be the entire collection of all variables and we denote the specific variables or features with x subscript 1, x subscript 2 and so on up until x subscript n. Which brings us to a second new notation, namely the letter n, which we will now use to denote the amount of features. In our case n is equal to 3. Also don't forget we used m to denote the amount of training examples or in other words the amount of rows in our dataset. In our case we didn't define the end of the dataset but let's say we have 23 training examples, meaning that m is equal to 23. Next, if we try to look to one specific training example, let's say the first training example. Then we denote it with x superscript 1. We can express this as an n by one-dimensional vector. Namely, this one. And if we want to specify the third variable in the first training example, we denote it by x superscript 1, subscript 3. In our case this will be 7578. So to summarize, we have x subscript j to denote the jth input feature. We have x superscript I to denote the input features of the ith training example and we have x superscript I, subscript j to denote the value of the jth feature in the ith training example. As we are now familiar with some terminology, let us look how to extend our hypothesis and cost function for multiple features. In fact, as we will see in a moment, this will be really easy. But before we do, if you found this video helpful so far and want to learn everything about machine learning and AI, please consider subscribing. That said, let us look to an hypothesis with 3 input features. As you see, it's nothing more than adding the features x1, x2 and x3 together with its corresponding theta parameters, theta 1, theta 2 and theta 3. There is just one odd thing, we now also add the feature x subscript 0. But what is this? We never defined a feature called x subscript 0. In fact, this is just the value 1, meaning that we can just multiply it with theta 0 so as you can see it's the same as just writing theta 0. Why we do this will become clear in a second. But first, let's generalize this hypothesis for as many input features as we want. Remember that n is the amount of input features our dataset contains, so we can write the hypothesis as follows. Running up from x0 up until x subscript n. As n becomes large, this can become a very long expression. This will make it really unpractical to work with, and also when we implement this in software it will become very unpractical to work with if n becomes larger. That's why we will represent all these different multiplications as a vector multiplied with a vector that is transposed. We can write this vector multiplication as follows. Theta transpose times x. With x containing all the x values and theta containing all the theta parameters. They are both vectors that are element to the set R, n plus 1. In practice this means it has n plus 1 rows and 1 column. Or in other words, the vectors run from x subscript 0 and theta subscript 0 up until x subscript n and theta subscript n. Next we multiply this x vector with the transpose of the theta vector. When we take the transpose of this vector, we get this. Which basically just gives you now one row and n plus 1 columns. if you don't understand or just need a refresher on vectors. The next video will explain the basic vector and matrix manipulations that you will need in this course. But in short, we can multiply these vectors like this. And as you see, it's exactly the same as our hypothesis. Now before we end this part, I want you to get a more natural feel of what the parameters theta stand for. Let's say we have this hypothesis, with x1 the amount of horsepower, x2 the age of the car and x3 the mileage of the car. We see that the hypothesis predicts that the base price of a car is $2,000 and for every additional horsepower, the price of the car goes up with some value. The age on the other hand will reduce the price of the car with some value, and also for every additional mile the car has, the price will also go down a little bit. That said, in the next video, we will see the basic vector and matrix manipulations we will need in this course. And it will become apparent that these vectors and matrices will have a very important aspect in the implementation of machine learning.